There we are.
All right.
Morning, everyone. Thanks for joining. Here to talk to you and share some thoughts on oh God, I hate this dingy thing. We need to switch to a better video conferencing platform. Here to talk to you about some of the work we've been doing on the IREE side and in the community to try to create a funnel for our ML front ends. So first, just a quick refresher on who I am and the team I work on. We're the IREE team at Google. We're working on CPU, GPU, compiler backend, and among other things, and are also making a fair number of investments in the ML front end landscape and whatnot, and trying to democratize this a bit. So what I'm going to present today is basically should be seen as findings that we've had from IREE, from going through the process of trying to connect different ML front ends together across tooling barriers. But the goal that we'll get to at the end is I would like to figure out the path forward that makes this, not an IREE thing. So next. This is a little bit of an opinionated viewpoint that we have on what a preferred ML compilation pipeline might look like. Very simplified. Basically what I'll be focusing this talk on is, what we're calling the input waistline. Basically, what's the concentration point that we can get to that lets us represent programs from a variety of the important present day ML front ends. I think one of the issues that we've run into in the past is that historically ML has been a rapidly expanding field, frameworks up and down all over the place, and it's been hard to get a lock on things, and you kind of keep things in different silos. This might be premature or not true, but my opinion is that for the present generation of what we have, we're fairly stabilized, across these things, and it's probably a good time for us to start talking about actually defining a waistline, the concentration point for real. So that's the point that we can debate and argue about. But I think that for the frameworks that we have on the left, there's a lot of commonality and that we should be able to exploit and make more interoperable.
Stella, just for context, can you just mention which part of this is slideware and which part of this is we kind of have it working and these are lessons learned from that?
Yeah, I will get to the lessons learned. This is me expositing my opinion so far, so I'll tell you when I get to the specifics. But
I didn't mean the lessons learned, but just which part of this is slideware and which part is built it.
So this part is, so all of this is built it. I do call out by exception the few things that we haven't exposed yet that I'll get to later, but this is effectively built. We are, and I know we're not the only ones on the IREE side are making this work in terms of from TensorFlow, TF Lite, PyTorch, JAX, and Onyx, concentrating down into a smaller set of dialects, which I'll show you in the next slide is not as nice as this picture, but is still a smaller set, and managing to compile things and run things. So that is working. What I think that I would get to is, sorry, got a little bit out of order on the slides, but is that I would like this to work better. So I'll jump forward a bit. If the previous slide was what I want, this slide is more of what we have, which is not quite a waistline so much as a kitchen sink, in my opinion. But maybe if we do the dishes and clean some things up, we can get more of a waistline, and then I can keep mixing my metaphors excessively, and we'll all have fun. So what we have today is a little bit more of we've got op-centric dialects in the waistline, TOSA, MHLO. We've got lower level dialects like LinAlg, LinAlgX, TM Tensor. These are having children at a prodigious rate that I would that is somewhat concerning to me in terms of if we're clearly having a friction and interface problem, and what happens is that people are reaching into internal dialects a lot to cross that boundary, and work is getting done, but we're not necessarily defining a good interface point. So stepping back a little bit to why I believe a waistline matters and why we should spend some time here. Ultimately, we have a desire for some degree of program portability and stability guarantees at this point. We would like the ability to not have a patchwork of tools that just help you getting from point A to point B. We would like a defined point that we can pull in from and then retarget to other things beyond that. This becomes practically important because at this boundary a lot, the question of versioning and serialization and extension management comes up a lot. If you've got a machine to machine boundary that is shared by multiple vendors and whatnot, you're going to have a hard time if it's a completely unstable interface for all of time. And so I think that becomes one of the forcing functions. And like I said, if we were to focus in this area and do something, it keeps the door open for retargetability of the compiler stack, retargetability of front ends, and gives us a degree of freedom on decoupling some of the system components that are currently kind of getting into larger and larger monoliths. And as someone who would like to see less monoliths and more connections, that's kind of where I'm going with this. So talked about this slide a little bit. The one thing we'll be talking about today is the IREE input dialect. And why we're talking about that is that the situation is not quite as dire as the previous slide would lay out in terms of all of the dialects that come together. When we have worked this problem forward for the different front ends between TF Lite, TensorFlow, JAX, Torch, rumors of Onyx, we've been able to converge on three things. One is that some of these are taking a path through TOSA for their core algebra offsets, and some of them are taking a path through MHLO for their core algebra offsets. What we did when we started on this journey was our converters were all kind of starting with MHLO or TOSA for the core set, and then we were just directly using a lot of ops and types from our internal dialects and just converting directly. So what we've done over the last year or so is extract out just the minimum set into our IREE input dialect, put that in its own project, and make it so that it's not so that IREE depends on that instead of the other way around, and then we target our converters at that. And I am making no claim in this presentation that IREE input is good or should be upstreamed, but I think that it demarcates a part of the space that we've not invested in, and that we should look at what's in it and then decide if we want to give this thing a name and develop it further. So covered this a little bit, what's in the IREE input dialect. So I covered this. I'm going to focus the rest of my talk on a quick survey of the bits that we put into the IREE input dialect, a bit of their rationale and why they're in there, and then focus on what's next. What can we do with this? What are implications for upstream? Here are some source links that you can look at and read along. Just a sec. So first, on the type side, I am not going to take the time to walk you through all of IREE's runtime type system. It's got a lot of types in it. It's got they're fairly low level, but these are the ones that we found were necessary to legalize arbitrary ML programs into. And you'll notice that this is more of a bias from IREE, that we model things up from a device and host buffer level, and then we wrap those in buffer views. So you can, if you're coming from another perspective, you can think of buffer view as like an indie array or a torch tensor or something like that. When we were doing all this, we were kind of annoyed that everything was getting called tensor, and we didn't do that. So, but it's effectively a mutable buffer. So the types we have are a buffer hierarchy, which IREE's internal buffers are more have more than this, but it's broken down between a bag of bits buffer that's focused on placement, and then a wrapper that is focused that adds metadata to it. You have a list type. This is one of the things that we found that is hard to do without and doesn't fit anywhere, and is pretty important for various front ends. Once you have a list, you've got to have a way to be able to model reference objects and variants and whatnot. So we have a variant type to represent the set of primitives and reference objects. And then we also have a somewhat possibly misnamed pointer object, which we use for doing indirection to globals. So no, that's the types. Details matter here. I'm mainly just trying to give you a survey of what's in here. One of the big things that that we have in here that gives us probably the biggest step up in expressibility is defined global ops, and we define these globals symbolically at the module level, and we define them so that they can contain a reference counted object, which happens to include buffer views, and they can be tagged mutable or immutable, and they're initialized either inline or via a module initializer. So that's long and short of it. If you're coming from a different domain, these are statics. You know, they're global. They're effectively global variables, and
well, Stella, it's also worth pointing out that here global is to the ML program being compiled. So frequently in applications, this is used for stateful models. So like a translation model or speech recognition model that sort of accumulates a state before pushing out tokens.
Yeah, we also use it for training, and we actually use it as the first step for lowering variables or mutable captures from the PyTorch side. And then, you know, we use it on the back end to determine whether it should be inlined into more of an inline constant, retained as a global, hoisted further. There's various things you do with this, but yeah, I wouldn't say it's just for stateful models. In fact, we use it for every training graph that we export, for example. And
well, I'd consider a training graph to be a stateful model.
Fair. So the specific ops that we have, you know, probably are not surprising to anyone who's done this before, but module level symbolic globals, the ability to turn a global into a pointer that we can then load and store indirectly, or we can do loads and stores directly on the symbol. And both of these modalities are used in lowering the full domain of tensor programs from ML front ends. Pause there. Some of you actually use this and may have thoughts. Okay. My goal with a lot of this, how is this different from a memref global? So one of the key things that's different here is that these are runtime types, and they hold reference counted into these, which, as near as I can tell, every real ML runtime is working with reference counted objects. And so I see memref global as a much lower level entity. It really you can try it, but we've had trouble actually modeling the faithful semantics of a source program just by kind of skipping layers and lowering directly to a memref global, which is essentially just a bag of memory, whereas the globals here are a holder for a reference type that may be a device placed buffer or other things.
Yeah, MLIR global is a much more specific thing. It's basically just like a global, like from like a C perspective, just a global memref descriptor. And so it's sort of just like a fancy pointer, and it has a number of limitations in terms of like, you can update the data that it points at, but updating like the descriptor itself, you can't just like swap it in for like you would have like a tensor object and like swap it into there. It's sort of one less layer of indirection than you need in practice.
Yeah, and it aligns well with memref global, aligns well with more of the kernel level of ML programs. It doesn't align well with more of the user level kind of as things are JITted or captured, because those are typically modeled on actual object references of some kind. We've also got some unsurprising ops that work on buffer views. Anywhere where you have a shape, you end up with rank and dim ops. So no big surprise there. Our list ops operate on the list type. In our model, lists are reference types or reference objects. Lists can contain lists, for example. Globals can contain lists, and they're basically trying to be the lowest level opinion-free way to contain a vector of object references or primitives. There's a lot of discussion when you get into this level of what about dicts and sets and queues and whatnot. And I do think that these are fundamentally different. You basically, if you look across the space, everything gets constructed with lists, and then you end up with much more algorithmic concepts on top of that, data structures that model things higher. So we put the list in the fundamental type bucket for this level of program, and then leave the rest for future elaboration. And some of you guys have used this. We use the lists on the TensorFlow side and various front end sides for representing how things are passed in and out of functions, which is often done via nested structs of various kinds. And then we use them on the PyTorch side as a thing that we lower the higher level torch concept of list into. And there's more elaboration to be done here. Mainly, key point is this is needed to have a full type hierarchy. Sean, did you have any other thoughts on this? Because you've used this.
No, I think that's basically it.
Okay. Sorry, looking at let me pull the chat up here. Yeah, lists are holding strong references to their elements, and basically, the thing that separates what I would call the ML programming domain from the lower level kernel generation domain is that the ML programs of the current vintage are all derived from reference counted object systems. So most of the ML runtimes start from that perspective. Like, we have a concept of reference counted objects, and we use that to move things around. And so we basically have pulled that concept in when we defined our lists. So the lists themselves do have a ref count, and they contain things that have a ref count, or they contain primitives.
So I think it's a little bit more fundamental than reference counting. I think it's that the front end languages that we come from allow memory and object references to escape. And so you don't necessarily need ref counting for that, but it is one way to implement that. And kind of the kernel generation level, kind of you're assuming that all buffers are generally pre-allocated and stuff like that. So I'd say that it's more about like lifetime management for escaping values rather than specifically reference counting. Although I do think reference counting is a very good choice in this context.
And turns out to be a universally made choice. So in this context. So yeah. Stephen, does that answer your question? Okay. Or Stefan, sorry, I misread who that was. So getting down into more of the minutia of opinions that we've taken just in this tour of force, I consider this part more optional and controversial, but I'm just covering it for completeness. We do have a set of tensor ops that we have that operate on tensors and buffer views for some of the primitive things that you need to do with respect to handling tensors, or which get transformed into buffer views later in our pipeline with dynamic dimensions. And yeah, so Alexander asks, is IREE predominantly designed to run models on a runtime, or can the model also be entirely compiled with a very, very thin RT? Good question. IREE basically is, and again, this gets into the specific hill we're trying to climb, is trying to be the thinnest possible runtime that fits the programming model, and even so thin that you just link it in. So, as an example, when we emit a C program from one of these things, it's just using freestanding C functions. There is no runtime for that are accessing some of the fundamental data types. So we use that on bare metal, for example, when we compile to bare metal to essentially make the runtime melt away. As you move up to larger and larger things, and you've got multi-device and whatnot, your runtime concepts take a bit more center stage, but they're the same thing. They're just a library-based assembly that that you're managing, kind of at the object level, like you would a low-level API. Alexander, does that answer your question? Okay.
Yes, thank you.
Okay. So, I mean, just to elaborate on that slightly, there's a lot of ways to hit minimalism on a runtime. We're trying to do that, and then have tried to expose then further what just the minimal concepts are up from there in order to target that minimal runtime, and that's really what IREE input became. So, the tensor ops, the key thread here is that at least at the time of authoring, we didn't have good tensor ops modeled upstream, and even today we don't have all of our tensor ops are what I would call shape erased, and that they basically depend on the shapes having come, or the dynamic dimensions having come through the data flow in some fashion, and that you can derive them either through some kind of inference mechanism or tracking through the IR or whatnot. What we have internally in IREE is that we have to convert anything that is in this implicit shape or dynamic shape erased world. We convert it into explicitly dimensioned, or it carries explicit symbols. So in order to bridge that gap, we sometimes need a set of tensor ops that take their unknown dimensions symbolically, just as freestanding index values. And so, as an example, the tensor reshape that in IREE input would be somewhat different than the tensor hypothetical tensor reshape in a higher level dialect like TOSA, because it's literally taking a variadic of its unknown dimensions, and these are all operating on ranked tensors, which is what IREE's runtime is the core of it is all about. So it would be a longer talk to explain why this distinction is important, and it would get into further theory and arguments on what the nature of dynamic shapes is. But suffice to say that IREE's opinion on dynamic shapes for ranked dynamism specifically is that every program that we legalize has to come in with all of its dimensions known and captured by the ops in some way. Either they're captured by the type, or they're captured as operands to the to the op as index values, and then as a consequence of that, we've found correct. These they don't rely on a descriptor of some kind packaged with the tensor itself. They don't rely that you're lowering to you might be lowering to a struct of some kind that contains that. So as a consequence of that decision, we end up with a set of tensor ops that are bridged around things. We use them at boundaries to functions, for example, to capture and concretize shape dimensions. We use them at the boundaries of custom ops, where at the lower level, you really don't want to be capturing a full DSL of what your shape program is. You just want to concretize the actual results of the shape calculation, and we use this set of ops to bridge that gap. Again, longer talk. Mainly just have it in here for completeness of, in the process of proceeding down that consequence of a descriptorless tensor at compile time that we can work on, we ended up needing these ops to bridge certain gaps. But this is more IREEs abstractions leaking, and we can argue about them later. And also in terms of completeness, IREE does expose some concurrency ops into its input dialect that can be programmed and accessed directly. We basically one of IREE's core concurrency primitives is a workgroup operation. It's not dissimilar to what you find in the GPU dialect, but we also use that for grid-based CPU scheduling, and that's been pretty effective for us. So we do expose that as something that you can actually form with your program. Again, IREE's abstraction is leaking a little bit more, but something that we found useful in lowering certain kinds of things or certain flows. So I'm gonna pause there. That ends the what did we decide to put into the bucket of IREE input. And I think that the main point I would make is there's not much there. Like, it's structural, some globals, some lists, some data types, some things that we found no other place to put them that really represent a program level tier of MLIR. And then there's some other things that have leaked out of IREE's abstractions that we can debate separately. But is there any thoughts at this level? Okay, so I've alluded to this, but I think that if I were to roll back time on this, we wouldn't have created IREE input. And my proposal is to not create IREE input upstream, but instead to make dir on something. So Siraj asks, regarding explicit rank tensors in ops, in our TOSA thinking, we see that certain ops may be rank insensitive versus others. Example, element-wise unary ops or output shape is whatever the input shape is. That's not the case with others, so the explicit term is tricky. Yeah, agreed. Like,
I find that only element-wise unary ops have that property, and absolutely no other op has that property.
So we could probably have another few hours of debates on the right ways to represent shape and dynamism, because we seem to have invented the cross-section of all possible ways. But let's not, like, I was more presenting that for completeness of, like, this is also something we found that was needed to get around certain corners. So if I was rewinding time on IREE input and saying, hey, I had perfect knowledge on how this was all going to work out from the ML front end perspectives, and maybe it was a couple years later and we weren't inventing all this stuff at the same time as trying to use it, I would really be focusing on solving the make dir problem upstream and saying tensor programs or ML programs are a thing that is consolidated enough at this point that what are we naming that? Where are we putting it? What kinds of things are going into it? And that's what I think we should probably roll the conversation back to. You know, I would use IREE input and the converters that have and the conversion flows that people are using in this space to represent whole models and whole programs as a prior that is basically says we have converged enough to build something here. You know, this isn't just unique shards in the ecosystem. We can actually create something more common. Yes. So Matthias asks, suppose I convert an ML program to input plus MHLO. If I store that to disk, how long would I expect it to work with IREE? Approximately however long it takes someone to submit a breaking change upstream. So, and that's really what gets me to why I'm having this conversation now. We were looking at investing more and more in armoring IREE input plus MHLO or IREE input plus TOSA or any of this stuff, you know, for better serialization guarantees and whatnot. And, you know, some words that someone shared with me once, that LLVM source instability has often been used in the past to drive people to upstream things. That rang in my mind as a, hey, we should talk about this. This is an instance of that. Like LLVM and the projects that we've created, the source instability is what's creating a longevity problem for these programs. And the solution, there are probably solutions to this by doing more upstream work on this instead of more sharding out to the individual tiers in the system. So to answer your question, not very long today, but I think that starting to define this waistline a little bit better upstream gives us the tools we need to start to have some more of those guarantees and reason about them over the years, you know, in a similar fashion that that, you know, LLVM has bitcode that has evolved in a direction that has allowed people to derive very strong guarantees from it. Does that answer your question, Matthias?
Yes, thank you.
Okay, so what I would do if I were starting over again, which I guess we are, is define an ML program dialect upstream. Literally do the Stefan. Ultimately, you do not want descriptors at runtime, really. And then the question is, when you erase them, we rely on LLVM to do this, blah, blah, blah. I'm not sold to do this at the interface waistline. Be excited to see some reference kind of buffers in first class thing in core. Just a comment, doesn't need an answer. I'll respond to that anyway. Yeah, I think that there's an argument to be had here. And I'm like, we should have that argument and figure it out. I think that we both agree on the reference counted buffers. And I will note that IREE does not exclusively target LLVM either. And that, you know, getting this in place and having the erasing be done at an appropriate level is fairly important to us. So
yeah, I mean, I think the answer to this is fairly simple, right? Because TOSA and HLO or MHLO are not shape carrying, and so I don't see any reason for anything else in the waistline to be required to be shape carrying unless it's like semantically relevant.
Yeah, I think it comes in around custom ops and so on, and then there's discussions that happen. But anyway, like I would like to create a forum where we can have this debate, and right now we're having this debate in a dozen different downstreams, and not because there's not a watering hole upstream where we even represent the program. Yeah, what I would do is I would solve the make a dir problem. You know, essentially my big idea in this presentation is hey, let's have a dialect, and in the absence of a better name, I would probably call that ML program. I would place that, you know, if I'm looking at the restructuring of the MLIR repo that Mehdi is pushing, the question comes up to me as to we have a targets directory which represent egress points from defined egress points and islands. Does it make sense to have a sources directory that lets us define ingress points that also are you know, represent an interchange point with the higher level instead of the lower level, and then I think that if we were to agree that that should exist, that it is useful to try to establish a waistline for the combined ML compiler runtime setups, then we decide on a name, we decide where to put it. We create a directory that has enough symbolic space in it to represent the concepts, and then we start populating it with the with just some of the basics to get going. So I wouldn't start by populating it with any of the things in IREE input. I would start by saying, hey, with the benefit of hindsight, let's define its real module. Let's define the functions. Let's have the debate on whether that's CFG or graph-based or both. Let's define what module initializers are, and let's start walking this stuff forward. This will take quite a while, but I think that that's fine, and that we should probably be looking in that direction. That's essentially what I wanted to communicate. Is I think that in all the developments that have been happening in downstreams on this to kind of move ML programming, more towards a compiled outcome. I think we are more converged than it would appear, if I was looking at that first slide that kind of just has everything in it. So Stephen asks, if these are mostly dialects, what do you think is different about sources compared to where other dialects would exist? So I've observed over time that there are at least 3 different approaches that I can find for flavors of dialects that exist in the ecosystem. Starting from the bottom, we have the egress dialects that need to conform to some existing system. Examples, and these are the targets of full conversions effectively. Examples of these include LLVM, SPIR-V, even MIT-C in its way. And so these egress dialects exist. We call those targets. And we accept a certain level of a lack of design freedom on those, right? Because your purpose is for getting out to some system. And then you've got the dialects in the middle, which we like to consider are basically completely open for design decisions. If there's a need to get rid of them, to change the lowering flows, to have a new one, we consider these dialects have no guarantees beyond the LLVM source stability guarantees, which are essentially you get to talk about it on the mailing list. And then so I think that's really valuable, that middle tier. That's where the compiler evolves, and we don't want to be mixing the internal representations of the compiler with something that we want to have stronger guarantees coming in. And so that's why I would probably put these in another category of their own and say these are source or interchange dialects that we've designed for some level of stability and eventual tools continuity for getting in and out of the compiler. They exist for the purposes of longevity and stability. And that doesn't mean that there's no design freedom there. It means that there are design constraints that we're putting on them that we're choosing in order to bias them towards low churn and low change and serialization, et cetera, et cetera. I think that my personal opinion is that LLVM evolved this concept with bitcode and without the benefit of dialects to represent this. So essentially, if you look at bitcode, it's representing a transformation layer there that is letting you get these guarantees. And I think that if you had dialects in LLVM, you might have solved it a little bit differently. And the problem in MLIR is actually much harder because we're not just trying to have a compatibility development flow for one dialect effectively. We need to effectively create the meta dialect and say this is a thing for this space that we want to have some further guarantees, and what are those. So I would do that by actually separating it and calling it putting it in a different thing, but it can just be like too.
So I guess to me, I think the difference is like going back to your LLVM MLIR analogy. To me, the LLVM MLIR dialect is something we have some freedom about, but the translation we don't have freedom about, right? So to me, the target translation is the thing that's fixed, and we pick the dialect to be useful, but we could have other things that use the LLVM dialect. So for instance, you could do binary machine code generation in MLIR. And so I think, I guess to me, I'm more of the opinion that kind of dialects are dialects, and maybe in general, we should be better about documenting which ones are really stable and which ones aren't, and
Yeah.
which ones are really mature and which ones aren't. But I guess I'd rather find a different way of doing that than source code organization.
Yeah, I mean, I can get behind that viewpoint as long as we do actually grow the distinctions in our mind. I think that we've been, been a little bit stuck in limbo on this for a long time in terms of without an idea of which dialects are even on a trajectory to evolve for stability versus are on a trajectory to be always considered a mutable concept. So
Yeah. I think maybe this also comes in with the versioning question, and I think this is something that Onyx has struggled with. For instance, is the dialect more stable than the thing you're translating from? And to some extent, my sense is that the philosophy inside Onyx, and maybe other people can correct me here, it is that the Onyx dialect is less versioned than the Onyx that you're reading, and so is kind of a little bit more of a stability layer that tries to abstract differences in different versions of Onyx.
Right.
And that there's a lot of regular concern about, oh, well, Onyx has changed slightly. How do we represent this in a portable way? Or does it end up introducing new concepts in the Onyx MLIR dialect that are suddenly version dependent?
I think there's a distinction here between things that have like an external referent, like an Onyx, like a serialized Onyx program or a serialized or an LLVM program or a TOSA program. For those, the dialect itself, like you said, is sort of like a convenience like, it's like, how do we get this in sort of the most software engineering way? I think for some of the context in this discussion, though, the dialect itself is, the interchange format. So like if we're going to have like a list type that we want to be able to, have a program that operates that and serialize that without like an external referent on, what that is, like the dialect itself has to be the point of stability. And so I think there's a slight distinction there.
I see. So you really want the let's say the MLIR textual syntax to be stable,
or a future serialization of it. I mean, TOSA takes this approach, for example, of I would love a serialization of it to be stable. That we can have a debate over time as to whether that is the literal textual serialization or not. But
yeah, we'd like to be able to do that. We aren't quite sure how to go about it. Sort of put a explicit portion into it.
So I can tell you that for us, I mean, it's really Onyx Standard that is the stable format, and we're really trying to limit the overhead, because as you have new operations, they often add a new parameters or something like this. If we just follow with an explosion of operations that handle each of those separate versions, it becomes really unmanageable, we believe. So that's why we really have, we try to introduce as few new operations inside of the Onyx dialect. Sometimes we have to, because a new operation is not compatible with an old one. Right. And then we have a version of it, basically two versions of it. But we try not to, because it just adds complexity. And for us, it is 2 releases or 3 releases of Onyx a year. So, I mean, it goes quickly.
I suspect that any desire to make things, to force things to be stable is kind of hopeless. I think this has to be kind of part of the versioning question, even if the version is, this is version 1 and we hope we never have to change it. You know, somehow embracing versioning at some level is a necessary evil.
Yeah, even if you change it daily, but you know that you changed it, that is a guarantee that is even helpful at some level. But yeah. So I think that, and then I'll get to Mehdi. I think that there is a difference between the practical stability guarantees that you get from more of the reduction dialects that are very ML ops centric. These are very centric on nouns that are evolving in research time effectively, versus we're even lacking the representation of the overall structure of some of these programs in a way that we can interop with tools. And I think that can be much more stable. And I would like to start getting that nailed down a bit. So Mehdi.
Oh, yeah, I think I agree with your last point also, that there are many levels of things to represent, and some can be naturally more stable. I wanted to come back to Onyx, and that may be more a question for Alexander, because you mentioned that in Onyx, when there is a new version of Onyx, you're going to try to not introduce a new op if you don't need to. But are you doing also the opposite, saying like at some point if you need a new op, another approach is to load old version of Onyx and upgrade them to the new op, so you don't need to model the old version of the op. In TensorFlow, that would look like there is like the usual suffix. There's going to be a batch norm v1, v2, v3, etc., etc. But internally, we can frequently upgrade a model that has the v1 to use the v2 instead, and so the dialect could only model the v2 part.
Oh, absolutely. We do that all the time. So, for example, if there's a new parameter that is added, then what used to be batch norm in your language v1, it becomes v2, and all the models automatically convert to add this parameter. So exactly. So our goal is to have as few version, and if we can convert, we do. If there's something that's fundamentally incompatible, then there's a few where we had to add different versions. And I also want to add that the Onyx community has put a lot more emphasis on converters. So there is also an ability to up convert as well as down convert, but we mostly use up convert older model to newer model. Yeah, absolutely.
And so the one thing about stability then is like what you described is also close to the LLVM model, where LLVM IR will evolve, but they keep the ability to upgrade all serialization, goes back with converter and things like that. But that's really compatibility at the interface, compatibility at the serialization layer only. And there are other questions about compatibility at a C API layer, or compatibility at a C++ API layer, which is even harder. So I wonder if to get those kind of stability, a dialect that we want, for example, if we wanted to expose, I don't know about TOSA, but if TOSA had a C API to create TOSA models so that frontends could directly use that, and you would want this to be very stable, you would likely have to manage it manually in this C API layer that is manually written and maintained. I probably wouldn't want to, like the difficulty would be to do what we do now, which is we use TableGen to generate a lot of interfaces, whether it's Python or C or this kind of thing. And then you're very coupled to both the dialect definition, which is a one-to-one to then what you generate, and the tool that generates things, because any change in the TableGen generation tool can change some details of your APIs. That makes it difficult. Whereas if you manually write your C API, then you can redirect to a new version of the dialect. For example, like we said, you can keep your batch norm v1 C API so that any frontend that was creating this in memory can still do it. But then you re-implement the C API so that in memory it creates the v2 of the up, and the dialect doesn't need to keep the v1 alive forever. I don't know who had their hand raised first.
I think it was Lay next.
Yeah. So my thought on this actually is like a plethora of different basically requirements. I have been working with like the stability side far enough. I mean, that's like a really hard boundary that you are crossing the hardware that you just like need to be stable. But for upper layers, to me, I think it's like less constrained there. I think one of the benefits of MLR is like the value propositions that if we can have this unifying being like the building blocks for various toolchains, that there is less requirements to really like have all the things serialized with the external format, especially for the upper layers, because like effectively you can basically pick the components and do like more the software side upgrade and stuff like that. So to me, like serialization format is more really for interacting with external systems that's entirely out of MLR. It's so hard to update stuff like that.
Yeah, I think there might be a downward-looking viewpoint and an upward-looking viewpoint of, you know, we're actively hemorrhaging on the connection points coming in too. So you know, have interoperability problems there that we would like to solve. If I could paint just what I wish we had. I wish we had a dialect that had these structural components, you know, leaving stability and versioning out of it, that represent the minimum set of things I need to get a wide swath of ML programs. You know, I've module func call initializers globals lists would go in here. I wish also that dialect had peer dialects like TOSA and MHLO. Onyx, is also qualifies as this, that I could draw on for the concrete ops and structure, or the ops and structured ops to represent the nouns of the program. And then I wish that I even had enough upstream that I could write, that if I sat down and said, I even want to build my dumb serialization v0.1 to carry us for a while, I have enough versioning information in those dialects and enough access to them in order to build that serialization layer. And currently I'm missing all of those things. So I think that what I'm proposing here is that we actually get the top level constructs in place and a development model that would let us build a serialization across a set of these dialects. So into that. Suraj?
I think you were first, Sean. Go ahead.
Oh, Sean.
I was just going to point out that, you know, in this discussion, you know, we're talking about CAPIs or on-disk format or whatever, and I think it's really, I just wanted to clarify at least what for me seems like the mental model is like, you know, there's two pieces. There's at a given point in time, what do we use in the compiler to, you know, represent and transform the program, and then there is, you know, an open set of across time versions of things that might be what we pull in from disk. And so like in this discussion, pulling from disk, or, you know, again, like Mehdi said, like the C API, maybe the C API is the thing that there's like multiple versions of it across time that we have to be able to, you know, link against and implement. And so I just wanted to point out that, you know, from this perspective, we want to think about, you know, like what is the thing that has to, you know, exist across time, and then what is the thing that we kind of get to decide. And so like in some contexts, we might want the dialect to be, you know, the thing that you actually serialize it and then like you can pull it off disk at any time. But sometimes what we want is the dialect is the thing that, and it sounds like Onyx does this, you know, it's like you like import the V1 thing as like V2, and then sort of the dialect itself is sort of like the upgraded version for that we want to really think about in the compiler at a given point in time. I just wanted to point out that mental model that was coming to me.
Suraj, did you still have your hand up, or was that from previous?
Yes, I do. I was going to make a point that serialization of a dialect is okay if the dialect itself is a self-contained expression of something, but that's not necessarily the case with TOSA, because TOSA has the mechanism to be able to support invocation of stuff that cannot be expressed within itself. So if you were to serialize it, there are points where you're sort of going to hand off to, maybe it could be a theory or something else, and serialization then becomes a problem of how do you serialize the other part of it. That's not TOSA. Yeah. So there's something, the mechanics of which I've actually been working on. I had an early conversation with Stella about this. I'll have a discourse out about it soon too. So that's there. So if it's not self-contained, then the serialization problem becomes what about other pieces that it's connected to? So it's MLIR after all.
Yeah, and Mehdi has dropped in recent thoughts on IR versioning. So we're about out of time. If I can land this, I would say that this is we're at the point where if we don't move some things forward here, we're going to just be having fragmentation for fragmentation's sake. And I would like to I'd like to figure out how to move that forward and who the people are that would be interested in defining a spot upstream to work this stuff out. You can either respond now or respond on the discourse thread when this goes out. But I would like to get a working group together where we could make some decisions and start to add some of the pieces that are missing.
Sounds good.
Okay, thanks, y'all.
Thank you, Stella.
So before ending, there is like a quick message I want to relay. There is an upcoming China MLIR meetup this weekend. So it's on Sunday. I think Jack is going to give an opening talk there. And then the following talks will be in, because it's a localized China meetup, it will be in native Chinese language. So if you are interested, please feel free to tune in. I will ask the organizers to post messages in the Discord soon later.
Thanks, Lei. Thanks for making that connection.
No problem.
Okay. Good weekend, everyone.
Take care. Bye, everyone.
Bye all.